All right, let's look at projectiles that are launched at an angle. So on our projectile motion part 2 notes, we had this problem here. We had a discus released at 40-degree angle, and it has an initial velocity of 24 meters per second. We wanted to know a couple of things. We want to know how long it stays in the air, and while it's in the air, how far does it go down the field? So what horizontal distance does it travel? All right, so let's look at what we have so far in our problem. We know that the discus is going up and over. It looks like a little rainbow as it flies down the field. We know that it was released at an angle of 40 degrees. And we know that it has an initial velocity at that angle of 24 meters per second. Now, one of the things that I told you about projectile motion is it's easiest if you separate it into its horizontal and vertical components. We don't want to look at it as one big parabola. We want to look at it as the discus goes up in the air and then back down. And then we want to look at it as the discus goes down the field. And so if we look at those two separately, it's going to make the process a lot easier. So the first thing that I want to do is separate the discus, the motion, into its x and y components. Now, for the y velocity, we want to use sine, because if you look at this angle that we've made right here, this little triangle, that 24 meters per second is like our hypotenuse. If you close that triangle in, the horizontal is touching our hypotenuse, while the vertical velocity is across from our angle, so it's opposite side. So we want to use the initial velocity times the sine of our angle. Okay, and the way that I got that, here's our angle of interest. The sine of my angle is equal to the opposite side over the hypotenuse. Opposite in this case is the Vy, and then the hypotenuse is my just plain old initial velocity, that's 24. So in order to get Vy by itself, I'm going to multiply both sides by that initial velocity. That will get rid of that. So Vy equals Vi, which is my 24, times the sine of my angle, which is 40. Okay, so Vy, for the velocity in the y direction, is equal to 24 sine 40. Okay, so I'm going to take that and put it in 24 times the sine of 40, and I get 15.43 meters per second, which is how fast it starts rising in the air. Once I let go of it and I start throwing it at this angle, it starts rising in the air at 15.43 meters per second. Okay, I also want to do the horizontal velocity, which will be very similar, except I'm going to be using cosine. So my initial velocity times the cosine of my angle will give me how fast that discus is going down the field. Okay. All right, so I'm going to use 24 for my initial velocity and 40 for my angle. So 24 times the cosine of 40 gives me 18.39 meters per second. So that's my initial velocity in the x direction. Okay, so let's figure out what we know for sure. Now that we've got a couple things that we know for sure, and I'm going to do my table with my x and my y values here. We want distance, VI, VF, A, and then time will be shared between the two. Okay, so in the y direction, our initial velocity right here is the 15.43 meters per second. In the x direction, our initial velocity is that 18.39 meters per second. Okay. Now, x direction, we could go ahead and say we also know our final velocity because it's the same. It's not going to change. Okay, so in the x direction, our final velocity is not going to change. All right, what else do we know? Well, we know that the discus is in the air. So in the y direction, we are going to have some acceleration because of gravity. Okay, now it's 9.8. If we're going on the way up, it'll be negative 9.8 because it's going to slow down as it rises. If it's on the way down, it'll be a positive because it'll speed up as it goes. So it really depends on what your reference point is if you want to make it negative or positive. I'm going to start here and go up. So I'm going to use negative 9.8. Now in the x direction, is there any acceleration? Nope. So there is no acceleration in that x direction. All right, let's start with the time. How long is it in the air? Now, very similarly to our horizontal projection, the thing that determines how long the discus is in the air is the vertical motion. Horizontally, if there were no gravity, then there would be no time that it would hit. The horizontal motion, if there were no gravity, then it would just keep on going and going and going. The thing that causes it to come back, to slow down and come back, is gravity. Otherwise, the path of our projectile would just look like this, to take off in outer space. Okay. So what makes it slow down and come back is our gravity. So our time is going to depend on these y variables. All right, so let's see what we know for sure. We know the initial velocity. We actually know the final velocity at the tippy top. You remember what that is? At the very top before it starts coming back, it has a final velocity of 0. Okay, so at the very tippy top of our path, before it starts coming back down, that final velocity is 0. So we know VI, VF, we know A, and we're looking for T. So we're going to use our formula VF equals VI plus AT. Final velocity is 0. Initial velocity, make sure you're using the y direction because that 24 is gone now. So it's 15.43. A is negative 9.8. And T is what we're looking for. That's our time. Now again, don't be tempted to take 15 and subtract 9.8. You can't do that because 9.8 is being multiplied by T. You have to work them one at a time. So what I'm going to do is pull that 15.43 over to the other side. Okay, then I can separate the 9.8 and the T. So I will do that by undoing that multiplication, dividing it. That's the opposite of multiply. And I get a time of 1.57. Okay. Now remember, that is the time it takes to get from here to here. But the discus is to come down too, right? What goes up must come down. So the total time of flight is double that, which will be 3.14. Okay, we have to double that 1.5 seconds to get the total time that it was in the air. 1.57 up, 1.57 down. All right, now we can look at the next part. Okay, time's going to be the same. You only have to write it once, really, because it's the same time. Let's look at how high it rises as it's going up. We want that height, that distance. So we know A, VI, VF for sure, and we want distance. So let's use our old friend VF squared equals VI squared plus 2A, and that change in distance. Okay. Our final velocity at the top is 0. Our initial velocity, remember use the red one, we're using red, so 15.43, and that'll need to be squared. Acceleration is negative 9.8, and we want to know how high it goes. Now I'm going to go ahead and make my DI 0 because that's going to be where the discus takes off from. So we're going to make that our starting point. That'll go away. All right, 0 squared is just 0. We'll leave that alone. 15.43 squared gives me 238.09. Okay, and we can't subtract that. We're going to have to pull this over just like we've been doing. All right, now we can get it away from the D. Okay, so our distance, our height, divided by 19.6 gives me 12.15 meters. Okay, so that's how high in the air it goes. Okay, our last little piece of this puzzle is how far down the field does it go? For that one, since we're working on how far down the field, working on our horizontal, we're going to use the horizontal values that we have. So we've got a velocity, it's the same velocity. We've got time, we want to know distance. So distance, df equals di plus vt. Let's scoot this down for a second. We want to know the final position, how far did it go. Our initial position, we can make that origin, that starting point, so it gets a 0. Our velocity is our horizontal velocity. Don't use our vertical. We're going to use that 18.39 now. And the time we just found, 3.14. Okay, make sure you're using the total time of flight because it's going down the field from here to here where it reaches the top of its path. And it's going down the field from here to here as it comes back down. So we're going to use that total time of flight to find out how far it went. So 18.39 times 3.14 gives us 57.74 meters down the field. Okay. So now, after only having 2 numbers, an angle and a velocity, well really 3 if you count acceleration because we know that too. After only having 3 numbers, we were able to find so much information just by using our formulas that we've got and figuring out the missing pieces of our puzzle. Hopefully this helps you with projectile motion. We will continue practicing with this, but if at any time you have any questions or need to go through a little bit slower, just please let me know.